Okay, we're going to try this again, but this time we're going to calculate heritability using data from twin studies. So I want to just review a couple of the concepts related to twin studies really quickly. So this is a page from your notes that tells you the basis of how we use the known relationship between monozygotic twins and the known relationship between dizygotic twins to estimate broad sense heritability. Now recall, broad sense heritability includes the effect on phenotypic variance due to additive genetic variance, dominance genetic variance, and epistatic genetic variance. So broad sense heritability is less useful for predicting the outcomes of things like selection experiments, but it still does give us an estimate of the degree to which the phenotypic variation among humans can be attributed to variation among genotypes. Okay, so what we do is we enroll large numbers of twins that are both monozygotic or dizygotic, those two categories. We're talking thousands of twin pairs, and we use those twin pairs to calculate the correlation coefficients in these two groups of a particular trait. I'm going to show you some examples of human psychological traits, but it could also be height or blood pressure or whatever you want. Okay, so this is a formula that is going to be on your formula sheet, but it's very, very simple. So this is the correlation coefficient for monozygotic twins, and this is the correlation coefficient for dizygotic twins. So let's have a look at some data. I'm going to go ahead and get rid of that layer, and we'll do some of these calculations. So I'll just rewrite that formula really quick. This is broad sense heritability is 2 times the difference in the correlation coefficients between monozygotic and dizygotic twins. This figure shows you all of that data. So here is correlation between twin pairs for a variety of traits, memory, neuroticism, that kind of stuff. And the black bars are for monozygotic twins, and the white bars are for dizygotic twins. These numbers are the number of twin pairs that were enrolled in that study. So this study, where we calculate the heritability of general intelligence, enrolled 4,672 pairs of monozygotic twins and 5,546 pairs of dizygotic twins, for a total of over 20,000 humans enrolled in the study, just to get you one estimate of heritability. So these studies are actually quite expensive to conduct. All right, so let's try to pull some of the data off of this chart and recreate, loosely speaking, some of their calculations so I can show you how that works. All right, so I'm going to get rid of this layer, and we'll write on this layer now. So let's say we want to calculate the heritability for generalized intelligence. So I'm going to rewrite the formula, and then I'll switch pen colors here really quick. And so my estimate right here for the correlation coefficient for general intelligence for monozygotic twin pairs, I think that's 0.85 roughly. Okay, so that's 0.9, so I'm just going to write 0.85. I tried to do this video once before and I messed it all up. Our correlation coefficient for dizygotic twins for general intelligence. Ooh, ha! Don't want to do that. Starts here. If I hold the shift key, it allows me to go straight. Somewhere just underneath 0.6. Let's say I'm going to estimate this at 0.59. It's just a rough estimate. If we had the precise data, it would be easier. Okay, so our heritability estimate is equal to 2 times 0.85 minus 0.59. Now, we could do that in our heads, or man. Somebody took my calculator and never gave it back. That's annoying. I have a cell phone. Don't forget your calculators for the exam. I just want to get this right because it's easy to mess this up. 0.85 minus 0.59 equals 0.26. Sorry about the noise. So that is equal to 2 times 0.26, which is equal to 0.52. And lo and behold, that's exactly what their estimate is. All right? So that's how you would interpret a figure like this to calculate broad sense heritability in humans for, in this case, it was general intelligence. Anyway, I hope that helps. That's another way to calculate heritability. This kind of estimate is useful for people like medical geneticists. If we have a new disease or something like that and we have calculated heritability to be 0, we know there's not really much going on in the way of genetic predisposition to the disease. A lot of human traits, though, have heritabilities in these regions, 0.2 to 0.5. We know that a great deal of interesting human genetic variation is caused by differences in genotype. The challenge is to find out what are those differences in genotype, what are the genes, and that's what genome-wide association studies are for. Anyway, I hope that helps. If you have more suggestions for me in terms of videos that might help you prepare for the exam and assimilate the information, just let me know. All right, I'm going to reach over here and try to figure out how to turn this off. Bye.